A resistor seems like one of the simplest electronic components. No moving parts, no amplification, no switching. So can a resistor generate noise? Surprisingly, yes. In the previous lesson, we learned that increasing receiver bandwidth also increases the amount of thermal noise entering an RF system. This relationship is described by the well-known equation P equals kTb. But where does this thermal noise actually come from? One of its most common sources is a component found in almost every electronic circuit, the resistor. This raises an important engineering question. How can a passive component with no amplification and no signal source generate electrical noise? Every resistor generates thermal noise, also known as Johnson-Nyquist noise, because the electrons inside the conductive material are constantly moving due to thermal energy. This random electron motion creates tiny fluctuations in voltage across the resistor, even when no external voltage is applied and no current is flowing through it. The noise is completely random and cannot be eliminated unless the resistor is cooled to absolute zero. The amount of noise generated depends on the resistor's temperature, its resistance, and the measurement bandwidth. Higher temperatures or wider bandwidths result in greater measurable noise. Intuitively, imagine a crowd of people standing in a room. Even if everyone is told to remain in place, people naturally make small random movements. Likewise, electrons inside a resistor are never perfectly still because thermal energy keeps them moving continuously. Physically, connect a resistor to a highly sensitive oscilloscope inside a shielded laboratory. Even with no battery and no input signal, the oscilloscope will display a tiny random voltage. That voltage is produced entirely by the resistor itself and is one of the most fundamental sources of electronic noise. Mathematically, the RMS thermal noise voltage across a resistor is given by Vn equals root of 4 kTRB, where K is Boltzmann's constant, T is the absolute temperature, R is the resistance, and B is the measurement bandwidth. This equation shows that increasing resistance, temperature, or bandwidth increases the measurable noise voltage. Noise generated by resistors is especially important in low-noise RF circuits. Matching networks, attenuators, bias circuits, filters, and many other RF components contain resistors that contribute directly to the receiver's overall noise floor. RF engineers minimize resistor noise by avoiding unnecessary resistive losses, selecting appropriate resistor values, reducing operating temperatures in specialized systems, and placing low-noise amplifiers before lossy components whenever possible. In extremely sensitive applications such as radio astronomy, satellite communication, and deep space receivers, even the thermal noise from a few resistors can significantly affect system performance. Understanding resistor noise helps engineers appreciate that every passive component can influence receiver sensitivity. Even though resistors do not amplify signals, they still introduce unavoidable thermal noise that must be considered during RF system design. A common misconception is that only active devices such as transistors and amplifiers generate noise. In reality, every resistor above absolute zero produces measurable thermal noise, regardless of whether current is flowing. In the next lesson, we'll explore the noise-temperature concept and learn how engineers describe receiver noise using the equivalent temperature of an electronic system. In this lesson, we learned that every resistor naturally generates thermal noise because of the random motion of electrons. We also introduced the thermal noise voltage equation and saw why resistor noise is an important consideration in sensitive RF receivers. In the next lesson, we'll explore the noise-temperature concept and discover another powerful way to describe noise in RF systems. If you found this useful, like the video, subscribe, and follow for the next lesson.